As we continue our discussion of energy, it's time to talk about light energy. Light can be thought of as energy traveling as waves. So that's one way to think of light. Here are a couple of waves. These waves down here have crests and troughs. All waves have crests and troughs, and they have nodes. The node is the point where the crest turns into the trough, the flip point right there, where the up becomes the down. That's a node. If we're talking about light energy, we need to talk about how lights of different colors are different, for one. Red light and blue light differ based on their wavelengths. A wavelength is the distance between identical points on successive waves. So here are two wavelengths that have already been measured. It's from one crest to the next crest, from one crest to the next crest. You could also measure from one trough to the next trough. This is a wavelength. You can measure from one node to a different node. One node, you got to skip that node to go to the very same node, meaning where the up becomes down, that's our starting point. So you got to go to the next point where the up becomes down. So this green line along the middle is a wavelength. All of those wavelengths are the same for the same wave. It doesn't matter what you measure from, but it's got to be from identical points. So this top wave has a longer wavelength than the bottom one. Okay. 400, red light is known as 700 nanometers. That's the wavelength associated with red light. And blue light has a wavelength of 400 nanometers. So if one of these is red and one of these is blue, the longer one is red light, the shorter one is blue light. Shorter wavelengths, blue light, longer wavelengths, red light. So these are lights in the visible spectrum. We're going to get back to that in a minute, but let's continue our discussion of red light and blue light as well. So wavelength is one thing, one property that we will use to talk about waves. Frequency is another property that we will use to talk about waves. Frequency is how many waves pass through a particular point in 1 second. So this wave is traveling across here. Yep, sound effects and everything. This wave is traveling, and if you put a marker at some certain point, and you measure how many waves cross this point in 1 second, that tells you the frequency. It really needs to be a straight line. That would be helpful, but, you catch my drift. So how many waves pass in 1 second? Frequency. In 1 second, fewer of these waves will pass than those. Because this wavelength is shorter, more of them pass in 1 second than this wavelength that's longer. Red light has a frequency of 4.3 times 10 to the 14th per second. And blue light has a higher frequency, a larger frequency, 6.6 times 10 to the 14th per second. One thing that I should point out, per second is also known as hertz. So when you see units of per second, that means hertz, or when you see unit of hertz, that means per second. Either one, they're both frequency units of measure. There's no conversion between the two. They are simply equal. Frequency and wavelengths are inversely proportional, meaning as frequency gets bigger, wavelengths get smaller, and vice versa. So we've talked about red light and blue light, which are both visible light types of waves, but these both fall under the electromagnetic spectrum. The electromagnetic radiation is energy transmission as waves. So red light and blue light fall under the electromagnetic spectrum, the electromagnetic radiation spectrum. But so do a lot of other types of light. Visible light is one type, but there are a lot of other types of light that are also categorized as electromagnetic radiation. All types of light are categorized as electromagnetic radiation. Oh, that is really difficult to say again and again. So here's frequency and wavelength. I should have said this prior to now. This V-looking thing is a Greek letter nu. That is frequency. Occasionally you will see that as a symbol F instead of a symbol nu, but it's a Greek letter nu in most chemistry textbooks. This is a Greek letter lambda, L-M-B-D-A, lambda. That is wavelengths. And I probably should have pointed that out prior to now. So we know the frequency and the wavelengths of red light and blue light as posted here. If I take and multiply those values together, multiply the wavelengths times the frequency, wavelengths times the frequency, I get 3.0 times 10 to the 17th nanometers per second, 3.0 times 10 to the 17th nanometers per second. I get the same value for both of these. This is the speed at which those waves are traveling. Blue light waves are traveling at 3 times 10 to the 17th nanometers per second. Red light waves are traveling at 3 times 10 to the 17th nanometers per second. All light is traveling at 3 times 10 to the 17th nanometers per second. Whether it's red, blue, or ultraviolet, or radio, or IR, all waves, all electromagnetic radiation waves are traveling at 3.0 times 10 to the 17th nanometers per second. So C, this here, is the speed of light. Speed. Again, this is not just visible light. This is all energy traveling as waves. Remember, that's what light is. So we will also see the unit in meters per second sometimes. Note that the initial value is the same. The only thing that changes is the exponent. We will most often use 3 times 10 to the 17th nanometers per second because visible light is in nanometers most often. But if you ever need the units to be in meters, you can use 3 times 10 to the 8th. Okay, so all light travels at 3 times 10 to the 8th meters per second, 3 times 10 to the 17th nanometers per second. Here is a spectrum, the electromagnetic spectrum. That's a listing of all types of light and light waves. There's gamma, there's X-ray, ultraviolet, visible, infrared, microwave, radio, lots of different types of waves that we see. These are all considered light waves. Which moves faster, X-rays or microwaves? That's a trick question. All of these waves travel at 3 times 10 to the 17th nanometers per second. Sometimes people think higher frequency means travel faster. Frequency times wavelength will always equal 3 times 10 to the 17th nanometers per second. Okay. So light isn't always thought of as a wave. There's this thing called particle-wave duality. Maybe you've heard that fancy phrase before. Light can be thought of as a wave, and we can calculate frequency and wavelengths and energy, actually, associated with those waves. But sometimes we also think of light as a particle. Albert Einstein discovered that light could be thought of as a particle when he did an experiment called the photoelectric effect. What he did was he shined light on metal surfaces. He shined blue light and red light on metal surfaces. And because we just talked about the wavelengths, see this blue is shorter wavelengths and this red is longer wavelengths? When he did this, when he did it on blue light, sometimes electrons got ejected, but not on red light. He observed that when you shine blue light on the metal, you get an electron that is ejected, an electron that gets ripped from your metal surface. Sounds like ionization energy to me. When he did it with red light, he got no reaction. There were no electrons that were ripped from the surface. When he shined a very dim blue light, he got electrons, but not many. When he shined a brighter blue light, he got a lot more electrons. When he shined a dim red light, no electrons. Bright red light, still no electrons. So from these experiments and more, he concluded, it must mean my light is not just traveling as a wave. It's not just behaving as a wave. It must be acting as a particle as well. A particle that he called a photon. What is a photon? It's a tiny particle of light. A photon, tiny particle of light. So when a photon of the right energy hits this metal, it ejects a single electron. One photon ejects one electron. They're tiny microscopic particles. Tiny particle of light, a photon, hits the metal and ejects one electron. So when he shined a dim blue light, he didn't have many photons hitting his metal, so he didn't have many electrons getting ejected. When he shined a bright blue light, he had a lot of photons hitting the metal, so there were a lot of electrons getting ejected from this. So, in order for an electron to be ejected, the photon must have enough energy to overcome the binding energy of the metal. It must overcome the ionization energy. You got to rip off that electron. So the blue photon does have enough energy. The blue photon has an energy that's greater than the binding energy of the metal, while the red photon does not. So what that also tells me is the red photon has lower energy than the blue photon. Let's keep talking about this energy thing. Energy is related to frequency. And so through those Einstein photoelectric effect experiments, he said the energy of a blue photon is greater than the energy of a red photon. He also knew that the frequency of a blue photon was greater than the frequency of a red photon. So since these have the same relationship, he said energy and frequency are proportional. So there was a different guy that came in and measured how energy and frequency are proportional. His name is Max Planck. He's a Swedish physicist, sorry. He measured this proportionality constant. He called it Planck's constant. We call it Planck's constant. You can call it Planck if you want to. Planck's constant has a value of 6.626 times 10 to the negative 34. So that's frequency times 6.626 times 10 to the negative 34 will give you the energy of the photon. What kind of units does H have? Well, energy, that's in joules. We've seen energy in joules and kilojoules and all that stuff. Energy is in joules. Frequency is in per second, also known as hertz. So if you need these units to cancel and equal joules, it must mean H has the units of joules times seconds, so that the seconds cancel and you're left with only joules. Okay. So we now have a few formulas with light at our disposal. C is equal to lambda nu. That's speed of light is equal to wavelength times frequency. We also now know energy is equal to Planck's constant times frequency. If you solve this one for frequency, that's C over lambda. So you can substitute that in here, and you can say energy and wavelengths have this sort of relationship. So these three formulas we will use quite a lot throughout Chapter 7 to talk about energy of waves and frequency of waves and wavelengths of waves. Okay. We're going to talk a lot about photons and such when we do this as well. Let's do a little problem with photons. Using light to initiate a chemical reaction is also known as photochemistry. So this reaction here is a photochemical reaction where we put in light energy, known as photons, put in a certain number of photons, a certain energy of photons, and you can break down ozone, that's O3, into O2 and a single O molecule. This is the energy required to break down a mole of O3, but this wants to know about a single photon. Not a mole of photons, a single photon. It's going to take a lot of photons to break down a mole of these atoms. Okay, so we take it back to our enthalpy plot days. We've got our reactants on one shelf, our products on one shelf, and I know this arrow should point up. Products should be above reactants because my reaction is endothermic. Give me a positive delta H. And I want to shine a light on this product, this reactant, to get me up to my products. That's if I shine a light on a single product, a single reactant, dang it, a single reactant that will get me to two single products. But what if I have a whole beaker of these things? I need to shine a ton of photons on there to end up with a ton of products, a ton of broken down ozone. It takes 107.2 kilojoules per mole to break down a mole of ozone. So how do I relate that to photon energy? It's simple conversions from here. So I know that delta H is plus 107.2 kilojoules per mole. But that's kilojoules per mole. I need to transfer it to single photon numbers. So if I have, how do I want to write this? So delta E is in the units of joules per photon, while delta H is in the unit of joules or kilojoules per mole. I simply need to make these things equal each other. So if I start with one single photon, because I want to know about one photon, let's transfer to say 1 mole of photons is 6.022 times 10 to the 23rd photons. Remember, mole is just a name for a number, and I bring in Avogadro's number of photons, and 1 mole of photons would require 107.2 kilojoules of energy. And I'm almost there. I need to know that 1 kilojoule is 1,000 joules of energy. So this cancels out everything to tell me the joules required for one photon, the joules required for one photon to react with 1 molecule of O3. So if I do that math, I get 1.78 times 10 to the negative 19th joules per photon. So I should get a very small number. A photon is a tiny particle of light. I should get a very small amount of energy that this photon is putting out. So delta E is related to delta H. All I need to do is divide delta H by number of photons in 1 mole of photons. That's all I did down here, to get delta E, joules per photon. And then a question that's behind all my writing, what's the wavelength of one of these photons? We will write it in a different color and try to not erase. If I know the energy is 1.78 times 10 to the negative 19th, I can know that energy is equal to hc over lambda. And I'm solving for wavelength, so 6.626 times 10 to the negative 34 joule seconds. This is joules. And then I'm running out of space, but this is multiply all on the top, 3 times 10 to the 17th nanometers per second, divided by lambda. And if I solve for my lambda, I'm going to put it here. It's real crowded. Solve for my lambda, I get 1,117 nanometers. And that's the wavelength of light needed to initiate this photochemical reaction. Okay, so if we draw a similarity between our enthalpy plots, delta H, our enthalpy plots, we had a 0 kilojoules line, we had a shelf that had reactants, and a shelf that had products. And anytime there was an arrow headed north, that was an endo. Anytime there was an arrow headed south, that was XO. And so overall, this reaction that I've drawn a transition for would be XO to go reactants to products. If we relate these enthalpy plots to Chapter 7, energy plots, in Chapter 7, we're not talking about reactants and products being on shelves. We're talking about electrons. And I'm going to write these little electrons as little dots. We're going to talk about them being dots or not dots later. But if I need to eject an electron, I can put in energy as light, and I can eject an electron. The electron has to overcome this threshold at 0 in order to be ejected. That's an endothermic transition. Energy has to be put in to eject that electron. I can also put in energy that promotes electrons. So if I put in energy and it happens to hit this electron down here, it can promote this electron to a higher energy level. It doesn't have to go all the way to this 0 point. It can promote an electron to a higher energy level. So frequently, when you put energy into an atom, a molecule, electrons get promoted to higher energy levels. These energy levels we will refer to as shells. So this is the n equals 1 shell, n equals 2 shell, n equals 3 shell, etc., and you can keep going up real high. But as you get higher, the energy levels get closer and closer together. My drawing up here does not show that well, but the next slide we're going to get there. So I can promote an electron from an n equals 1 to an n equals 2. I can promote it from an n equals 1 to an n equals 3 if I put in the right kind of energy. I can promote from 2 to 6 if I put in the right kind of energy. I can promote from 1 all the way out of the atom if I put in enough energy. So let's look at some of these. These shells have associated energy values. So the value on the y-axis for this n equals 1 would be negative 2.18 times 10 to the negative 18 joules. The value for this n equals 5, negative 8.72 times 10 to the negative 20. That tells you how far away from this 0 line the shells are. So these particular shells have this energy value because they're associated with a hydrogen atom. So there's a formula, an equation that says I can determine the energy of a hydrogen shell, a hydrogen shelf, with this equation, negative RH 1 over n squared, where if you're trying to determine n equals 6 level, you put in a 6 right there. And RH is known as Rydberg's constant. It's a constant. It's 2.18 times 10 to the negative 18 for a hydrogen atom. So Rydberg's constant times 1 over the shell you're trying to calculate the energy of, and that gives you the energy value of that shell. So if you plugged in 2, you would get 5.45 times 10 to the negative 19. Plug in 4, you get negative 1.36 times 10 to the negative 19. Yeah. So using this equation, we calculated all these energy levels. Okay. This video is getting pretty long. I still got quite a bit more to say. The transition from n equals 4 to n equals 6, is it endo or exo? Well, n equals 4 to n equals 6, that's going from here up. It's obviously endothermic. You got to put in energy to make that happen. The transition with the longer wavelengths of emission is n equals 6 to 2, that's this one, or 4 to 2, that's this one. So there's 4 to 2, highlighted in green now. Well, it's asking about wavelengths, and this is an energy plot. Energy is equal to hc over lambda, so as energy gets bigger, wavelength gets smaller. Energy bigger, wavelength smaller. Or as wavelengths gets bigger, energy gets smaller. They are inversely proportional. So longer wavelengths, I'm looking for smallest energy. Smallest energy, 4 to 2. Yep. All right. The last question on here. The transition with the greater frequency, N3 to N1 or 5 to 3. Here's 5 to 3 highlighted in green. So energy is equal to H times frequency. So as the energy gets bigger, the frequency gets bigger. The greater frequency, we're looking for greater energy. Greater energy, that means the longer the line. So that's 3 to 1, obviously. All right, a couple more questions on these energy diagrams. here are energy levels of a hydrogen atom. These. How many emission lines would be observed in the emission spectrum as a result of these transitions? Well, for every transition, every down arrow, you observe an emission line. These emission lines are not all in the visible region, but you observe an emission line for each of these transitions. So all I got to do is count the arrows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I would see 18 emission lines in this spectrum. So I said not all of them are in the visible region. In fact, only the Balmer series is in the visible region. Red, green, indigo, and purple all appear in the visible region, but everything else are not in the visible region for hydrogen. Okay. The emission line with the shortest wavelength would result in the transition from 7 to what? Shortest wavelengths and energy are inverse, so shortest wavelength means biggest energy. Biggest energy means longest line. Obviously, that's 7 to 1. Yep. So if we scoot right along in our discussion of energy, we said previously the energy required to remove an electron from an atom or a molecule is known as the ionization energy. We said we can put light energy into a system to rip an electron away from our atoms. So if I put in light energy, I'm going to put in light energy that's got this much light energy. That's a great way to say that. When I put in that amount of light energy, it's going to get me above the threshold to pull an electron off. It's going to give me more energy than is required to pull an electron off, but energy is always conserved, So this transition is known as my ionization energy, but this leftover energy is actually kinetic energy. So as I rip away that electron, the electron starts moving away, and I can measure the kinetic energy that this electron has as it's moving away. So if I know that I put in photons of a certain energy, this is the light energy being put in, photons being put in, and I can measure the kinetic energy of the electron as it's moving away, I can determine the ionization energy of any given atom. So ionization energy is equal to the photon energy minus the kinetic energy of the electron that's being ripped. Yeah? That's how I can determine ionization energies of tons of atoms, tables and tables of atoms, ionization energies. So I said we can think about these energy diagrams as having electrons in them. So if I put in a photon energy that's this amount, that photon could rip an electron from the n equals 1 shell, and it would give me a kinetic energy of this little red arrow. But when that photon comes in, that photon could hit an electron in the n equals 1 shell, but it could also hit and will also hit an electron in the n equals 2 shell. The blue line, the photon energy, is the exact same, but the ionization energy required to rip an electron from the n equals 1 is greater than the ionization energy required to rip an electron from the n equals 2. And I can measure that in a lab by measuring different kinetic energies of the electrons that are removed. Smaller kinetic energy tells me that electron was closer to the nucleus. Bigger kinetic energy tells me that electron was further from the nucleus. The reason being, smaller kinetic energy means more energy was required to rip it away. Bigger kinetic energy, less energy was required to rip it away. Whew. So this is the kind of spectrum that I get out of this. This is called a photoelectron spectroscopy, PES, photoelectron spectroscopy. So if my kinetic energy, this is a kinetic energy scale, if my kinetic energy is smaller, it's telling me that electron is closer to the nucleus. If my kinetic energy is bigger, it's telling me that electron is further from the nucleus. Watch the x-axis on this plot. Sometimes we will see it plotted as kinetic energy, A lot of times we will see it plotted as ionization energy, so it should be different. Ionization energy, this would be the big ionization energy. This would be the small ionization energy. Ionization energy and kinetic energy are inverse. Okay, so this tells me I've got mostly two sets of peaks, which tells me I've got two sets of shells that electrons came from. The height of these peaks tell me how many electrons are in that shell. So these heights are pretty much the same, but if I integrate under here, actually, there's more area under this curve than there is that one. So that's how I get there are 2 electrons in this shell and 3 electrons in that shell. One little nugget before we really wrap this thing up, because we are long-winded today. This is officially 2 separate peaks, which tells me that I've got 2 shells that are really close together. We're going to refine our definition as we move along, but they really are 2 shells that are very close together. That gives me 2 peaks that are very close together, but we're not ready for that refined definition yet. We're going to call those things subshells when we are ready for that refined definition. Okay, here's our photoelectron spectroscopy instrument. Doesn't it look fancy and giant? Yeah. Remember, we know how much energy we're putting in with a photon. We know the measured kinetic energy. We can determine the ionization energy that was required to rip out that electron. Here's a pretty complicated PES spectrum of xenon, because xenon has a ton of electrons. We're going to see much simpler PES spectra in our connectivity and problem sets, but we're using these electron spectrums to determine the organization of electrons within an atom. That's what we're using all this for. I have talked way too much, way too long. I hope you kept up and paid some attention. It should be a fun afternoon. Goodbye.